This episode is sponsored by Audible.
In the last decade alone, thousands of new planets have been discovered orbiting distant alien suns, many of these far larger than our planet, called super-Earths. But would these super-Earths be super places for humanity to colonize and settle? To my perpetual irritation, a lot of popular science articles tend to report every new exoplanet of note with a great deal of hype, and one such example is referring to super-Earths as Earth-like in ways that imply we could move on to one tomorrow. This tends to be justified by them being both Earth-like exoplanets we found, so I thought for today we would discuss why that is, what super-Earths are, if life could naturally evolve there and get technological, and if we have any interest in colonizing them ourselves. Now, when I was a kid, planets numbered 9 and fell into 2 categories: rocky inner planets and big gas giants, plus the freak planet, Pluto. Folks were always looking for Planet 10 or Planet X, which wasn't always being used as the Roman numeral X or 10, and already debating if Pluto should count. Indeed, we had previously had more than 9 planets, as we used to count the bigger asteroids like Ceres and Vesta, and even before we found our first exoplanets and the additional dwarf planets in our own solar system, there was a lot of talk about how to reclassify planets. We knew that our catalog would expand enormously and that we would doubtless find thousands of planets closer to each of our planets than they are to each other, and we theorized many more. So the classification systems themselves are very broad and ill-defined, with many suggestions and many overlapping. That's part of the problem with sensationalist headlines, is there's not really some official list of what is what, as it's still early days with little knowledge, and I would say if anything, the astronomical community is even more hesitant about defining planet categories after the whole Pluto fiasco. The other part with sensationalist headlines, besides that publications are rewarded for overutilizing clickbait, is that often when we discover some new planet that is no more like Earth than Mars or Venus is, or even less so, it gets listed as the most Earth-like exoplanet yet discovered, because this is actually true. The thing about exoplanet hunting is that your odds of seeing and confirming a new exoplanet mostly rely on how close it is to its new sun and how big it is, as both affect how much light it reflects or blocks or how much gravitational impact it has. What this means is that while our basic models say there will be more smaller planets than bigger planets, our observations mostly consist of what we call hot Jupiters, giant planets near their sun. There are probably a dozen or more dwarf planets like Pluto in our solar system, and that's likely a common thing in the galaxy, but such tiny ice dwarfs, low in mass and far from their parent stars, are going to be the last things we discover and properly inventory, much as they are in our own solar system. Sometimes we only know their radius, not their mass, though we can make decent approximations of the latter from the former, and an icy world Earth's radius but Pluto's density is not going to be livable, as it would evaporate if we warmed it up with terraforming. So too, a planet right near its sun, of Earth's radius, is likely to be as dense and unlivable as Mercury, but is the first Earth radius planet you would expect to find. Very loosely, we tend to guess stars hosting planets between half Earth's mass and double Earth's mass, and getting maybe 25% more or less of our solar illumination would likely be present in at least 1% of solar systems, and maybe as high as 1 in 10 or more. They should not be rare, but we've discovered very few less massive than Earth, and of those more massive, those 1,500 and counting exoplanets of more than 1 but less than 10 times Earth's mass that we call super-Earths, virtually none would be even as promising as Mars or Venus for terraforming. Again, not because we think they are rare, just that we see big, bright, and hot exoplanets easiest, so currently if we find one of Earth's radius, it's usually Mercury distances or closer, and if we find one at Earth's distances, it's probably either a giant planet or around a giant star making it too hot. Now we are finally getting a decent list of planets whose mass, radius, and lighting does not make the word Earth-like sound too absurd, but while Earth-like mostly meant hot super-Earths, we had a lot of speculation about colonizing those, and I thought we should start our own by discussing the composition. Now that might seem like a strange point to begin on, given that the broadest of the category, simply being more massive than Earth, but not more than 10 times as much, leaves a huge range for composition, But we do not really live on Earth. We live in that tiny band of its surface that's got air and water. By default, we'd expect a bigger planet to have these too. Indeed, given that our concern about terraforming low-gravity planets is their atmosphere escaping, we would generally tend to expect more massive worlds to have thicker oceans and atmospheres. And here's where it can get confusing to folks. See, if I tell someone we found a world twice as big as Earth or twice as massive, folks tend to think I said the same thing, and that it would have twice the gravity Earth does. Earth is actually the densest planet in our solar system, though roughly tied with Mercury and Venus only a bit behind that. But Mars is 71% of Earth's density, and so a Mars-dense but Earth-sized world would have a surface gravity of 71% of Earth normal. And by the way, for folks new to the show wincing at me repeatedly garbling the pronunciation of Earth this episode, my apologies. For some reason, even after years of speech therapy, I can't seem to properly pronounce the name of the planet I live on. Anyway, so long as the radius stays the same, the surface gravity is proportional to the density. A Plutonian world with a density a third of Earth's would have a third of the surface gravity if Earth-sized, so would have a real problem holding on to any atmosphere. And indeed, given that it's a big ball of ices, many of which would be gas, not liquid at room temperature, such a planet could not plausibly exist in a habitable zone of a solar system. It would melt and boil away. However, for some context, a planet of such density could still have Earth-like gravity. It would just need to be 3 times wider than Earth, and at a third density, contains 27 times the volume, but only 9 times the mass, right near the top of what would be a super-Earth, but more in line with what we mean by the term mini-Neptune or ice giant, such as Neptune is now considered, or even a gas dwarf, a rocky planet with a thick atmosphere. If you are curious, the lowest density planet in our solar system is Saturn, just about an eighth as dense as the Earth. And at 95 times our mass and 9 times our radius, its nominal surface actually has about the same gravity as Earth's, just a bit higher. This is one reason we sometimes contemplate building a shell around such planets, moving them closer to the Sun, and terraforming that shell. You would get an Earth-like planet with 95 times our surface area. So we want to be mindful that even inside our own solar system we would already see a wide variety of masses and densities and sizes that make it very clear a planet's mass or radius being close to Earth's does not mean much for habitability, and we're only talking size and density and mass thus far, not if it is around a redder sun or hotter overall or has a nice sized moon. A planet twice as wide as Earth and of Earth density has twice the surface gravity and 8 times the mass. A planet twice the mass of Earth, but the same density, is only 26% wider and 26% stronger surface gravity, the cube root of 2 incidentally. Was it thrice the mass and the same density, that radius and surface gravity would be the cube root of 3, 1.44, or 144% of Earth's, rather than 126%. But at 200% the mass and 126% the radius and gravity, this isn't really what we mean by a super-Earth. It's in the range, but on the smaller side. But let's consider this world for a moment, which we will nickname SFIA-26. First, all things being equal, it could be a bit further from our Sun and still be habitable. The bigger the planet, the warmer it's generally going to be, again all things being equal, though do not assume we're talking Venus hot at Earth distances or habitable out at Mars. Super-Earths are likely to have a slightly wider habitable zone around their star. Wider surface too. 26% more radius means 58% more surface area. Here's where we get a problem though. Imagine we just teleported Earth's atmosphere right to this world. Well, it's got 58% more area to cover, so that doesn't work. Not enough air. Ironically, that's not true, but to explain that, let's imagine we just gave it 58% more air, the same air above each square meter of land as Earth has. Now what? Well, the gravity is stronger, so that air actually gets mashed down more. You need less air on such planets to achieve normal surface pressure because of that higher gravity, and a place like Mars needs more air for its lower gravity for that same reason. Mars lost its atmosphere and oceans because of its lower gravity and lack of magnetosphere. Such a big planet has more gravity and probably more molten core for a bigger magnetosphere, helping prevent loss. But again, proportional to its surface area, it would actually need less air to match Earth's air pressure. However, surface gravity isn't the same as escape velocity. As I mentioned, Earth and Saturn have comparable surface gravities, but Saturn is nearly 100 times more massive, and its escape velocity is 4 times higher, which makes a huge difference in rates of atmospheric loss. Our hypothetical small super-Earth with twice the mass and 126% the radius and surface gravity of Earth has 126% higher escape velocity too. For our audio-only listeners, I've got the equation up on the screen for anyone wanting to calculate various hypothetical planets themselves, but I'm intentionally keeping to the math-intuitive ones for today when possible. Now, how a planet gets its initial oceans and air is a complex and still mostly mysterious matter. We guess Earth had its own proto-atmosphere blown off when the Moon formed and recollected from comet bombardments later on, but in a basic and oversimplified approximation, we could assume a planet started with air and water proportional to its total mass. If we made Earth 26% wider and 58% bigger in land surface, but it started with 200% more air and water, then it's got 26% deeper seas and 26% more air per square meter, both of which are under higher pressure from that increased density and higher gravity. On Earth, you need to drop around 10 meters deep or deeper in the water to add an atmosphere of Earth pressure. On SFIA 26, that pressure is up after just 8 meters. Earth's average ocean depth is 3,700 meters, over 2 miles, and has a pressure down there of 370 atmospheres. Here on SFIA 26, the average ocean depth, all things being equal in continent layout, having just twice as much water over 58% more surface area, is 4,700 meters or 3 miles deep. And the pressure down at that depth isn't 470 atmospheres, but rather about 590. Of course, it will probably be higher because it probably has a lot more air sitting on top of that ocean too. But also, Earth is constantly losing air, mostly hydrogen gas as it's the lightest, to atmospheric escape. Such a planet should have less escape. This is part of why the gas giants have so much hydrogen. And how much hydrogen you have controls how much water you have, as oxygen is plentiful and slow to escape. So you probably have more air and water than we factored in already. Now the next issue. If Earth's seas rose from 3,700 meters to 4,700 by a whole kilometer, not much Earth would be left poking above the water. And again, we would actually expect more water depth on this world from that slow hydrogen escape, and maybe even its gravity tugging more comets into it down the eons. Now, there is still a lot of land above a kilometer in altitude here on Earth, and we are not just talking about mountain peaks. Eyeballing an altitude map makes it look like about a quarter of our land, big chunks of Central Asia, Southeast Africa, and the western US are, and generally it's those places like the Rockies and Himalayas, the newer mountain ranges, that are resulting in those large chunks of livable but high altitude land near them. Keep that in mind for in a moment. Here on SFIA 26, that might mean it had a quarter of the proportional land to Earth, but it's got 58% more surface, so about 40% Earth's land area. Again, probably less than them having less hydrogen escape, and more water as a result, but let's stick with that for the moment. No problem imagining them getting a good-sized civilization from that, and spaceflight is harder because of probably much thicker air and higher gravity, but not implausibly so. We've talked about a parallel case before for habitable high-gravity worlds, and we need to remember they also need stronger, thicker, or denser bones for land life, which might prevent or slow life coming from the seas too. It took us a long time to get animals out of the sea onto the land. For the overwhelming majority of Earth's history and life's history, there were no land animals. That need for strong endoskeletons and shoulders and hips and such might mean it took another billion years to crawl out of the seas, out into the tidal pools, and then to live on land, or that it never did. Speaking of tides though, another thing to keep in mind is that Earth used to spin a lot faster. The moon has been slowing our day length a little each year for eons, and back in the day it was 12 hours long and had much stronger storms. Faster planet rotation means worse storms. Erosion of land would have been much more severe. If such a planet began with a faster rotation and had no huge moon to slow that rotation, and a bigger moon than our own giant one. But thicker air itself makes for stronger erosion. And moreover, stronger gravity favors flattening too. Every volcanic eruption needs to fight that much harder to get high land. Every grain of dirt tumbling downhill in a breeze or rainstorm or river has that much more force acting against drag of the land to keep it moving downhill before friction stops it. Stuff just wears down more, and stuff does wear down. Again, most of our higher altitude lands are near those newer mountain ranges. SFI A26 is generally my basic example of a high gravity board. It's getting in that range of Earth-like planets where it's definitely colonizable and terraformable, but where you might need to be mega nuking the ocean floor to get yourself some new land, or building pontoon continents, which is certainly an option. Layers of small hollow cylinders full of air stacked into vast rafts kilometers long to build houses on is no more effort for living space than kilometers of overlapping domes, or giant hollow cylinders orbiting the planets that people live inside, those O'Neill cylinders we're so fond of discussing here as alternatives to planets. You could make some very large and durable islands out of layers of pontoons, and if the galaxy turns out to be full of lots of oceanic planets, this might be a common approach to settling them. Nonetheless, SFI A26 is getting close and maybe already passes by where we'd expect a world to be Earth-like, and where it's a bit dubious not if life could form, but if it could evolve to be either land-dwelling or even photosynthetic. I'll explain that more in a bit, but in the absence of photosynthesis, you would not expect the sheer quantity of biomass and biodiversity we tend to assume is needed for intelligent life to arise. This is why we don't tend to expect to find anything particularly impressive in subsurface oceans on frozen moons like Europa, even if we do find life there. For the moment though, as I said, SFI A26 is not really a good example of what we mean by super-Earth. It's on the low side, but I think it fits what most folks are thinking of in terms of gravity and such. I want to consider several other cases, and let's start by just scaling up to 8 Earth masses, near the top of super-Earth sizes and another math-convenient one, and we'll dub this ward SFI A200 since so many of its qualities will be 200% of Earth. Its surface gravity, escape velocity, and ocean depth for starters. At Earth density, this is a ward twice as wide and with 4 times the surface area, which in our basic approximation means its oceans are 8 times larger in volume, spread over 4 times the area and thus twice as deep. There is very little of Earth that's more than 3 kilometers above our current sea level, and all that gravity and thick air is not helping with high land masses forming or not eroding away. By default, we would expect this to be a blue world with little to no land above water, and maybe not even in the first couple hundred meters of depth where sunlight reaches. With the nutrients all deep down and the sunlight far above, life can certainly form near thermal vents if that theory of origination is true, but getting it near the surface to survive on light is hard, with all the nutrients sinking down. We examined this case in more detail in both our Ocean Planets episode and our episode looking at if technology couldn't develop without fire, and looked at some other options like subsurface air pockets or floating icebergs with captured dirt or ash as places life might take hold, thus I don't want to focus on it too much today. Additionally, we are only at first approximation here. We do not know that there are not factors shoving that water down under the crust into the mantle where it gets stored, we think as hydroxide in minerals such as ringwoodite. I'm sure most of you have heard how we believe much if not most of Earth's water is in the mantle. That's both accurate and off, as it isn't in water form. Folks hear that about the mantle and wonder why it doesn't come rising up since rock is denser than water, but ringwoodite is about 4 to 5 times denser than water for instance, and it's got the hydrogen and oxygen, not an actual H2O in it. For that matter, water or water ice can be pushed into forms nearly twice as dense as normal water, like Ice 7 at 1.7 grams per cubic centimeter, again see that Waterworlds episode. So there is a lot that could prevent a world just being covered infinitely deep in water, and that matters because any planet that is bigger than Earth and not much closer to its parent star ought to have a lot more hydrogen than us. It is incredibly common after all, it just blows away easily. Water, its most common molecular form besides diatomic hydrogen, is absurdly abundant throughout the universe, as is oxygen, coming in right after hydrogen and helium in elemental abundance, albeit a distant third, and forming the important part of the air we breathe, the majority of the mass of water we are mostly made of, and the most abundant atom in the rocks we stand on. So what other weird factors should we consider? Well, before segueing off water, it's worth noting that a planet mostly composed of water, but Earth-sized, would have the same gravity as the Moon's surface, and would have to be 5.5 times wider than Earth, with 30 times the surface area to have Earth-like gravity. Though on such a world, the pressure would be high enough to force collapses into some of those denser ice types, even if it had no significant amount of rock. We shouldn't discount encountering some water giants in the gas giant ranges though, closer to the sun than all gas giants are. Low density might be decently common too. A super-Earth of 10 Earth masses but Mars density would have 14 times the volume of Earth, 240% of its radius, and about 560% of its surface area. We will call this one Ares 10, and its escape velocity is still only double Earth's, more mass but less dense, and it might not have much of a magnetic field given that the density implies it's low on iron at its core. We are contemplating natural worlds for the moment, see our Mega Earths episode for truly enormous Earth-like worlds we made ourselves, such as the Saturn shell I mentioned earlier. One might imagine such a world as Ares 10 forming nearer its sun and having a fairly tepid magnetic field, thus being fairly Mars-like, arid and dead instead of water-rich, but one could equally imagine finding such a world that had a good mix of seas and shore to produce a fairly Earth-like world except for the high gravity. One thing to note though is that at higher pressure, chemistry often acts differently, and biochemistry maybe even more so, with many gases we consider benign acting more like acid. So those are our biggest worlds, low density and high mass. The reason we would not expect to find worlds much more dense than Earth already is simply because even a world made of pure iron is only 42% denser than ours, and we would not expect to ever see such a thing nor an entire planet of those rare elements denser than iron. You could get denser, but we would probably need to assume special conditions, like a punishing sun or a collision event even worse than one we think made our moon that just stripped off everything lighter than iron. Weird results from collisions is certainly not something we can rule out though. Heck, you might even get hoop worlds as a result, which are technically super-Earths, but we will visit them another time too. As mentioned, we think Proto-Earth got whacked by something Mars-sized to result in modern Earth-Moon pairing. Uranus, 15 times Earth's mass, is tipped over on its side, and we tend to assume a similar event caused that, and probably also caused Venus to be all weird with its slow backward spin and day longer than its year. We might imagine a large planet near its sun getting baked off lighter elements, a hot Jupiter turned a Chthonian planet, then hit by a dwarf planet of more normal composition that shoved it into a more livable orbit too, and covered its surface with a thin layer of lighter elements, water, and air. We could imagine a super-Earth with a Mars or even Earth-mass moon around it as a near-double planet, potentially savagely tectonic and with no shortage of land. We could imagine a collision that resulted in increased spin, rather than slow spin like Venus got, so the world actually bulged noticeably at the equator. We could even imagine some combination of that which resulted in a world like Paramundia from the sci-fi novel Duty Calls, where the planet's equator is nearly open magma and the rest desert, except for ultra-high plateaus scattered around that, having varying pressures and climates based on the altitudes of various plateaus, where stuff migrates around on wings or even by being living blimps. The more massive the planet, the more likely we are to have an abundance of hydrogen and helium for such things. You could have stuff living on parts of super-Earths that were lower pressure than Mount Everest, and others at air pressures Earth never sees, even before getting to ocean life. Such planets could have quite a collection of moons too. Remember, we are talking about worlds often closer to Neptune and Uranus in mass than Earth, each with a dozen moons, and Earth-sized planets probably would have more moons in most cases where they didn't have big ones like ours does. Very large rings are possible too, potentially like Saturn even. One very likely scenario would be such worlds existing decently further from their sun than Earth, either on more elliptical orbits or just being colder. Less heat, less water over ice, less erosion, potentially offering ice-covered worlds of mountains and valleys, with warm but darker oases below, and brighter UV-blasted cold thin air spots above, and many climates in between on the slopes and in the caves of ice. You could go further too. We have underground lakes in Antarctica, and we think subsurface oceans are decently common with large and colder moons. So a rare super-Earth out past Mars might have vast amounts of tidally heated underground lakes and caverns. And those buried lakes in Antarctica do contain life, so it's not a huge stretch. In this very same way, there's nothing stopping some large world, a Chthonian or nearly so, becoming tidally locked near its sun, especially in the case of a red dwarf, and potentially instead of being bright desert on one side and dark tundra on the other, we could see molten slag on one side and icy mountains on the other, and a wide band of habitability on the equator, or even again by altitude, deep down below the punching sunlight in the valleys, between ancient dead but enormous volcanoes, breathable at the bottom but near airless at the tops. Super-Earths run an almost unimaginable spectrum of possible worlds, from paradise to graveyard, molten cinder to icy rock, but amid all of those, it is possible life might arise no different than here, eventually growing clever and reaching out to space. As to us colonizing them, I would say not without much modification to cyborg or transhuman, or extreme genetic engineering, at least for those whose gravity was half again our own or more, but we will have to see, and that's no bar either. I suspect though we would still rather build our own cylinder habitats with gravity and air pressure and temperature of our choosing, rather than try to set up giant pontoon island habitats on some oceanic super-Earth. Of course, if life originated on such a world, smart dolphins with technology for instance, and they got to space, they might prefer building entirely marine habitats, giant cylinders full of water, as might we to help preserve our own marine life, and it's trickier than it sounds. We will examine oceanic space habitats next week though. For now, with super-Earths, our imagination is our only real limit because we still know so little about how planets form, or what the catalog of exoplanets really is out there in the galaxy. One thing's for sure though, with us discovering hundreds of new worlds a year now, we won't lack for a shortage of examples to investigate. A few minutes ago I was mentioning Paramundia from the sci-fi novel Duty Calls, where they got a blasted landscape below and many huge mountain plateaus everyone lives on, and the comedic central character of those novels, Commissar Caiaphas Kane, spends an awful lot of time traveling to strange new worlds and trying not to get killed on them, and it was long a favorite series of mine that didn't have any audiobooks. And the publisher, Black Library, has been moving an awful lot of its content into audiobook format finally, and has put a lot of effort into making those some very top-notch performances, often with full casts rather than a single narrator. That series is a great example of science fiction and satire, so I am retroactively awarding it our January Audible Audiobook of the Month. Those are all available over on our sponsor, Audible, and usually for less than half the price they retail at. As I often say, a good narrator can make a good book great, and a great narrator can make a great book even better. And you get a lot of impressive talent narrating audiobooks these days. I was rewatching Lord of the Rings with my wife recently, who hadn't seen any of the films before, and afterward I picked up the newest edition of the audiobooks, and those are narrated by Andy Serkis, who was the actor who played Gollum in those, and his talent and versatility in voiceover really elevates the performance. If you're looking for reading materials during the winter months, and before the new TV series comes out, J.R.R. Tolkien's Lord of the Rings, Hobbit, and more are rightly considered the best the fantasy genre has to offer, so I'm giving that the Audible Audiobook of the Month for February. Now, Audible is the place to go for audiobooks, but it has a lot more to offer, including many excellent podcasts, such as Science and Futurism with Isaac Arthur. That's right, our show is available on Audible now, and that includes the narration-only version for folks who prefer to skip on the music we blend into the episodes, which seems popular for folks who like to drift off to sleep listening to me, though the Audible Plus catalog also has sleep and meditation tracks available, as well as guided fitness programs for helping keep those New Year's resolutions, and Audible originals like Neil Gaiman's Sandman Act 2. In fact, they have so much content that if you hit the play button, it would run for a few centuries before anything repeated, including about 500 hours of this show now, and the whole Audible Plus catalog comes as a bonus when you join Audible, in addition to your usual one free audiobook each month and big member discounts on additional ones. And as always, new members can try Audible for free for the first month. Just go to audible.com/Isaac or text Isaac to 500 500. So today's topic was super-Earths, and as we mentioned today, there's a chance those might be entirely oceanic. And next week we'll examine some megastructures and space habitats built with marine habitation in mind, including a new ultra-large megastructure option we have not examined before. Now, such megastructures take huge amounts of mass to build, and sometimes more than an entire solar system might contain of a certain element. So we'll go into March looking at nuclear transmutation options for civilizations that don't want to wait on supernovae to get more materials. And of course, such megastructures often assume lifespans similar to the planets they emulate. So on March 10th, we will take a look at how you could build a machine designed to last 1,000,000 years. Then we'll have our March Sci-Fi Sunday episode to look at the concept of synthetic life. Now, if you want alerts when those and other episodes come out, make sure to subscribe to the channel and hit the notifications bell. And if you enjoyed this episode, please hit the like button and share it with others, and leave a comment below. You can also join the conversation on any of our social media forums, find our audio-only versions of the show, or donate to support future episodes, and all those options and more are listed in links in the episode description. Until next time, thanks for watching and have a great week.